Let's go over Chapter 4.1, Investigate Square Roots and Cube Roots. Determine the area of each square shown. Record the info in a table. So the left side here, we know that the length of this square is 1. Therefore, this side has to be 1. Same thing here. If this length is 2, because it's a square, this side has to equal to 2 as well. And so on. So let's first fill in the blank for the side length here. The column is 1, 2, and 3. But recall back to our area equation. Area of a square is equal to length times width, or sometimes you are taught base times height, or you might also know side times side. This is more for squares. So if we use side s times s, then this can be rewritten in s squared form. Therefore, we can fill in the middle column there, area of square in exponential form. Oh, by the way, exponential form just means use the exponents like that. 1 to the power of 2. The area of a square with a side length of 2 has to be 2 to the power of 2. And then last one is 3 to the power of 2. We can conclude that the area is 1, 4, and the third row is 9. So what is the relationship between the side length of a square and the area of a square? It just means that the side lengths are squared. Moving on to the bottom half. Determine the volume of each cube shown. Record the info in a table. So cube, the definition of cube is that it's a 3D shape or 3D figure with the equal side length. So if we are given that this side is 2, then this side here is also 2, and this side has to equal to 2 as well. When we're looking for volumes, oh, actually, let's go over this one first. So if this length is 3, then this length has to be 3, and the height has to be 3 as well. Before we move on, I would like to address what the formula is for the volume of rectangular prism. We can say that volume equals to the length times width times height. But with the cube, so volume of cube, we can actually just shorten it by saying either length times length times length because they're equal, or we can just use a different variable, s for sides. And then we can rewrite this into the exponential form, which is L cube or S cube. Depending on which variable you choose to use, please specify before you go straight into the exponential form so I know what you're talking about. So from the table here, side length, when the side length is 2, the volume of a cube in exponential form would be 2 cube, or 2 to the power of 3. So the actual value of 2 to the power of 3 is 8. For the last row here, side length of 3, the volume of a cube is 3 cube. and this is equal to 27. The new term, a perfect square, is a number that can be expressed as a product of two equal factors. Product means multiplying, okay? So, for example, 9 is a perfect square because we know that 3 times 3 is 9. Okay, same idea gets applied to the perfect cube. So a number that is a product of three equal factors. So 64 is equal to 4 cubed. Therefore, 64 is a perfect cube. Complete the table showing all perfect squares and perfect cubes up to 10. So first, let's fill in the number column. So 4, 5, 6, 7, 8, 9, 10. And when we're filling in the perfect square column, I would like you to try writing this in the exponential form first and then evaluate it. That means that we're looking for 4 squared equals 16. And so on like that. 5 squared equals 25. 6 squared equals 36. 7 squared equals 49. 8 squared equals 64. 9 squared equals 81. And lastly, 10 squared equals 100. For perfect cube, it might be a little bit more tricky, but you can just watch what I read, or you can try putting into your calculator to double check. So 4 cubed is equal to 64. 5 cubed equals 125. 6 cubed equals 216. 7 cubed equals 343. 8 cubed equals 512. 9 cubed equals 729. And 10 cubed equals 1000. Square root is one of two equal factors of a number. For example, 9 is a perfect square. So if you square root that 9, you're going to end up with 3. It has to be two equal factors, so you just take out one of a pair. Cube root is one of three equal factors of a number. By the way, 8 is a perfect cube. You can kind of see that from here. Therefore, cube root of 8 is equivalent to 2. Let's look at some other roots. 4 times 4 equals 16. So the square root of 16 is just 4. Or we can actually use a notation of square root. This square root of 16 equals 4. Cube root of 125 is, and we can double check up here, cube root of 125 right here is equal to 5. And forget this, there's a typo here. So cube root of 125 equals 5. So when we're using the cube root, there's a tiny 3 on top of the root sign, and that is called index. And unfortunately, we are not going to go over a lot of radicals, but just understand that that little number indicates how many numbers you're trying to take out. For example, square root is trying to take out one of 2 equal factors, whereas cube root is trying to take out one of 3 equal factors. Okay, so that little number is checking for how many 3 of a kind can we take out. Lastly, 2 times 2 times 2 times 2 equals 16. So the fourth root of 16 is 2. Because there's 1, 2, 3, 4 2's. The product of those 4 2's are 16. So fourth root of 16 is equivalent to 2. And you can see that the index has changed to 4 because they were looking for the fourth root. Moving on to example 1. Evaluate each power without using a calculator. So part A, 3 squared, we know that's just 3 times 3, so 9. Part B, this is equivalent to saying negative 3 times negative 3. And we know negative times negative is positive. So we have positive 3 squared, which is 9. You can just drop that positive sign and just keep 9 there. Part C. Now notice that this square sign is not for the entire negative 3. The base is just 3. That square is referring to that 3 only. This can be rewritten in a different way, that it's negative in the bracket 3 squared. That's an equivalent statement. We can say this is just negative 9. Part D. 3 cubed is 27. 3 times 3 times 3 is 27. And part E, negative 3 to the power of 3. So notice that the base now is negative 3, not just 3. So we are saying this is equivalent to negative 3 times negative 3 times negative 3. There's 3 negatives. So when we are multiplying, negative times negative becomes positive. Positive times negative is negative. So we have to have a negative number. Now we're going to multiply the magnitudes of it. So 3 times 3 times 3, which is 27. So basically negative 3 all to the power of 3 is negative 27. F. And again, this exponent is only referring to the base 3. So let's rewrite that so it's clearer. So this is just saying negative, and inside a bracket, 3 to the power of 3. This is equivalent to saying negative 27. Example 2. Evaluate each root with a calculator. First step as putting in the 8 in first. And I don't know what kind of square root button you have, but you'll probably have something like this button, or you're going to have this button, or you're going to have some kind of rectangle like that under a root sign. So either or. So just plug those in and then press enter or the equal sign. Second brand might be a little bit different. Some calculators like the user to input the square root 1 first. And then you press 8 after. It totally depends, so you need to understand how your calculator works. So if you were to plug it in properly for the part A, you're supposed to get 2.828. So if you didn't get that using the first method, try the second method or vice versa. For part B, when you're inputting, you might have to use a bracket around that -8 to make sure that negative stays with that 8. Unfortunately, when you plug that in, you will get an error message. It's because you cannot take a square root of a negative value. And we'll discuss that in a bit. Part C, cube root of 8. When you plug it in, you might have to look for a different button, but honestly, that's okay. We're not going to use that as often, so let's just do it by hand. So we know 8 is a perfect cube, so we can say that's 2 times 2 times 2, which is, and the index is 3 here, so there's 3 of a kind, so we're taking 1 out. So the answer is 2. All right, now you see the negative here for part D. So cube root of negative number is a little bit tricky. So before I said in part B, I said you can't take a square root of a negative number. For part D, I'm gonna show you mathematically why this is possible. So I know 8 is perfect cube, but also you know that -2 times -2 times -2 is also -8. Isn't that 3 of a same factor? So we could just take 1 out. So that's equivalent to having -2. Example 3. What happens when you evaluate 4th root of -8 and 5th root of -8? So the negative number within the radical, the square root or the root, is really tricky. So normally we say we first expand the inside the radical, and then we're going to look for the index number of same factor to take out. Just like part D, even if it was -8 inside the radical, we were able to find 3 of a same factor and then take 1 out. Let's take a look at the 4th root of -8 and see if we can do the same thing. So 4th root of -8 can be rewritten in an expanded way, but then we can't write this into a power, some base to the power of 4 equal to 8. So I'm just going to keep it as 8. And let's actually take a look at the negative, and then maybe we'll multiply -1 multiple times. Let's try it. So we know -1 times -1 is positive, but we need to make sure that our number inside the radical has to be negative, just like -8 here. So we're going to multiply -1 once more. But I need a 4 of the same kind. This is a 4, the index is 4. So I'm just going to have to multiply one more 1, -1. But now this is positive. This won't do. Unless 8 is negative. But I'm taking -1 out, whereas -8 is still inside the radical. So this won't do. By the way, when you actually punch this into your calculator, you will get an error message just because the negatives doesn't go away under the radical, therefore it's invalid. That being said, when we take a look at the fifth root of -8, it's a bit different. This time we can actually expand this into -1 times -1 times -1 times -1. And now this is positive, positive, right? So we need one more -1. Hey, we have the fifth -1. And then we can keep that 8 positive. How about we take 1, 2, 3, 4, 5. We have a 5 pairs of -1. So we can take that 1 out. So we can say it's -1 times fifth root of 8, which is equivalent to -fifth root of 8. And this value actually exists. It's not an error. It actually exists. Part B. Is there a pattern as to when you can evaluate the root of a negative number? Well, from previous example 2 and 3, we kind of noticed that square root of a negative number wasn't defined, but cube root of negative number was defined. Same thing from example 3. Fourth root of negative number was undefined, but fifth root of negative number was defined. So I guess the only difference was either the index was even or odd. So we can explain that even number index versus odd number index. I would like to kind of show you why this is true mathematically. All right, so square root of a negative number, we can just say, let's say it is defined, then we'll have, for example, some number is equivalent to square root of a negative number. Let's say -1. Let's try it. So we can kind of tell that when we're undoing it, we we square both sides to get rid of the square root. That's reversing the step. We would get x squared equals -1. But is it possible to have a squared of a number that is a negative number? This statement is invalid. So for example, negative times negative can never equal to another negative value. And this is why this statement this is why the statement fails. Okay, whereas let's say x equals cube root of -1. We're gonna cube this. Cube this. So we're gonna cube both sides, and we're left with x cubed equals -1. Is it possible to have some number cubed to get -1? Yes. X is just -1 because -1 times -1 times -1 is -1. Also, I forgot to mention it for the squared version here. I said negative times negative can never equal to negative, but also positive times positive can never equal to negative. X has to be either both positive or both negative. So in this case, you can kind of see that it's not possible for us to square a number to get a negative value. Now let's take a look at prime factorization. It is the process of writing out a number written as a product of its prime factors. Right, so for example, the prime factorization of 12 is 2 times 2 times 3. Or we can just say 12 equals 2 times 2 times 3. Also, because we now know how to use exponents, we can say it's 2 to the power of 2 times 3 equals 12. Let's try example number 4. Find cubic root of 729 using prime factorization. We can use factor tree. So first take out the radicand that's under the root sign. So we'll first write 729, and then we're going to divide this. We're going to split this up into a product of prime numbers. So because the last digit here ends with 9, my guess for this is that let's try dividing this by 3. So we write the 3 there. And when you take 729 divided by 3, you get 243. Now, we're going to continue this, but except our branch cannot go any further for this one because it's a prime factor. It's a prime number, therefore we cannot divide this any further. So we leave it there and just focus on the other branch. So this time also, because it ends with 3, I'm going to try dividing this by 3 again. So 243 divided by 3 is 81. So this is done. So we're going to leave it there, move on to 81. 81, you can say, hey, I know that. That one's just 9 times 9. You could recognize it, but if you didn't, that's okay. And this time, 9, you can kind of see that that's a multiple of 3. Same thing as here. So those are the end of the factor trees. We're not done yet. The cubic root of 729. So we need to rewrite this like that in the expanded version. So let's rewrite 3's all in one. So 3 times, how many 3's are there? 6 3's. 3, 3, 3, and 3. All right, and then we're gonna take a look. Last lesson, we talked about how index here tells you how many of a same kind we're trying to take out. So here we can say that there's 3 3's and another 3 3's. So we can take one out from each group. We get 3 times 3 outside of the root, and then you can rewrite the rest. But notice that this is just equal to 1. So we can just say 3 times 3 is 9. All right, moving on to example 5. Evaluate each expression without using a calculator. I will only work on part A, and the rest of this question will be for homework. All right, let's take a look. The first thing we would do is that simplify the square roots if we can. So we have 49. We know that that's 7 times 7. We also know that 36 is 6 times 6. So we can say, we can rewrite that 2 times in a square root, 7 times 7 plus 6 times 6. And then we can count. By the way, the square root has a default little 2 there. We just don't write it, but it's there. So we can take out one of the pair and one of the pair because they're the same numbers. So let's take out 1, 7. And because we took that out, there's only 1 left. So we're not going to write it because square root of 1 is just 1. And when you're multiplying 1, it really doesn't do anything. All right, here you go. And then plus we take one of the pair out, so we have 6. So this equals to 14 plus 6, which equals to 20. So you guys could work on the rest of this example.